Hello everyone, welcome to Math Side Trips, a channel for math teachers, students, coaches, trainers, and enthusiasts. Thank you for sparing time and effort to visit this channel. Many of the topics that have been discussed and will be discussed in this channel are those that are not usually taken up in mainstream classroom instruction. We hope that you will find in this channel something new, interesting, or useful. So this is our channel name, Mathematical Side Trips. In this video, discussion will focus on the construction of equations in one variable, in particular equations involving absolute values of the types absolute value of ax squared plus bx plus c equals dx plus e, and ax squared plus bx plus c equals px squared plus qx plus r. In a preceding video, the equation of type absolute value of ax squared plus bx plus c equals d has been discussed. So now we consider the next two types, which I have mentioned a while ago. Okay, the type absolute value of ax squared plus bx plus c equals dx plus e. Here we keep in mind that dx plus e must be at least 0. Before looking at the method of construction, let us consider the following example. Find the solution set of the equation absolute value of 7x squared plus x minus 74 equals 4x plus 26. So solution, removing the absolute value sign, we obtain the equation 7x squared plus x minus 74 equals 4x plus 26. And the other one, 7x squared plus x minus 74 equals negative 4x minus 26. From which we obtain 7x squared minus 3x minus 100, which is the product of x minus 4 and 7x plus 25 equals 0. And the other one is 7x squared plus 5x minus 48 equals the product of x plus 3 and 7x minus 16, which is equal to 0. And hence the solution set is the set containing the numbers negative 3, 4, negative 25 over 7, and 16 over 7. One way of construction is by considering a factorable quadratic expression and splitting the x term and the constant term as a sum or difference of two other terms. Example, construct a type B equation from the expression 7x squared minus 3x minus 100 equals x minus 4 times 7x plus 25. So here, the x term and the constant term is minus 3x minus 100, and we rewrite it as 8x minus 11x minus 67 minus 33. And from this we obtain the equation absolute value of 7x squared plus 8x minus 67 equals 11x plus 33, which has at least two solutions, which are x equals 4 and x equals negative 25 over 7. Another method of construction of this type is describe in the following theorem. Let ax squared plus mx plus n and ax squared plus bx plus q be two factorable quadratic expressions with real rational coefficients and constant terms. Then there exist real numbers b, c, d, and e such that the equation absolute value of ax squared plus bx plus c equals dx plus e has at least two real and rational solutions. Proof: let b be 1/2 of m plus p, c 1/2 of n plus q, d 1/2 of m minus p, and e 1/2 of n minus q. Then from ax squared plus bx plus c equals dx plus e, we have this expression on the left side and this expression on the right hand side, which simplifies to ax squared plus bx plus q equals 0. The left hand side expression being one of the given factorable quadratic expression in the theorem. And this equation has two real rational solutions since the left hand side is factorable. On the other hand, from ax squared plus bx plus c equals negative dx minus e, we have this expression on the left side and this expression on the right hand side, and the whole thing simplifies to ax squared plus mx plus n equals 0. Again, the left hand side is the other given quadratic factorable expression in the theorem. And this equation has also two real rational solutions. Again, only those solutions which satisfy the condition dx plus e at least 0 will make it to the final solution set. Still, another way of constructing this type of equation is shown in the next theorem. Let ax squared plus bx plus c equals dx plus e times bx plus q. Then this equation, absolute value of ax squared plus bx plus c equals dx plus e, or the other one, ax squared plus bx plus c equals bx plus q, has at least one real and rational solution. Proof: considering only the first case, in which the right hand side is dx plus e, so we have, after removing the absolute value sign, ax squared plus bx plus c equals dx plus e. And the other one, after removing the absolute value sign, we have negative dx plus e on the right hand side. And from the first equation, we have dx plus e times bx plus q minus 1 equals 0. And from the second, we get dx plus e times bx plus q plus 1 equals 0. Then the possible solutions are negative e over d, 1 minus q over p, and negative 1 minus q over p. Again, solutions that will satisfy dx plus e at least 0 will constitute the final solution set. Example number 7, find the solution set of the equation absolute value of 15x squared minus 22x plus 8 equals 3x minus 2. So, removing the absolute value sign, we have 15x squared minus 22x plus 8 equals 3x minus 2. Or the other one, 15x squared minus 22x plus 8 equals negative of the quantity 3x minus 2. From which we obtain these two equations, 3x minus 2 times x minus 1 equals 0, and 3x minus 2 times 5x minus 3 equals 0. So there are three solutions. However, since the solution 3/5 is less than 2/3, then the final solution set is the set containing only two elements, namely 2/3 and 1. So now we take up the next type, which is the absolute value of ax squared plus bx plus c equals px squared plus qx plus r. A convenient way of construction is by splitting a given factorable quadratic expression as a sum or difference of two other quadratic expressions. Example number 8, consider the quadratic expression 28x squared plus 23x minus 15, which is the product of 7x minus 3 and 4x plus 5. So it's a factorable quadratic expression. And then we write this as a difference of two other quadratic expressions. In this case, the quadratic expression 31x squared plus 25x minus 11 and 3x squared plus 2x plus 4. And from this, we construct the equation absolute value of 31x squared plus 25x minus 11 equals 3x squared plus 2x plus 4, whose solution set is the set containing the elements negative 5/4, negative 1, 7 over 34, and 3 over 7. Amazingly, when we write the same quadratic expression 28x squared plus 23x minus 15 as the difference of two different quadratic expressions, in this case 35x squared plus 18x minus 12 and 7x squared minus 5x plus 3, and consider the equation absolute value of 35x squared plus 18x minus 12 equals 7x squared minus 5x plus 3, we obtain another solution set containing four elements, which is the set containing the elements negative 5/4, negative 9 over 14, 1/3, and 3 over 7. However, random splitting of a given factorable quadratic expression does not always produce such a nice result. Another method of construction is described in the next theorem. Let dx plus e be a common factor of the two quadratic expression ax squared plus bx plus c and px squared plus qx plus r, where the absolute values of a and p are not equal and the absolute values of b and q are not equal. Then the equation absolute value of ax squared plus bx plus c equals px squared plus qx plus r has at least one and at most three real rational solutions. Proof: let m of x be the other factor of ax squared plus bx plus c, and n of x the other factor of px squared plus qx plus r. Then if ax squared plus bx plus c equals px squared plus qx plus r, then we have this equation dx plus e times m of x minus n of x equals 0. And because of the conditions that the absolute values of a and p are not equal and the absolute values of b and q are not equal, the x coefficients of m of x and n of x are not equal. Hence, the difference m of x minus n of x is a linear expression whose zero or solution may or may not be a solution of the given equation. Thus, there is at least one solution. On the other hand, if ax squared plus bx plus c equals the negative of the quantity px squared plus qx plus r, then we have the equation dx plus e times m of x plus n of x equals 0. Again, because of the same conditions, the x coefficients of m of x and n of x are not negatives of each other. It follows that m of x plus n of x is a linear expression whose zero may or may not be a zero of the given equation. Considering all possibilities, there is at least one and at most three real rational solutions. Example number 9, construct an equation of the form absolute value of ax squared plus bx plus c equals px squared plus qx plus r, one of whose solutions is x equals 5 halves. Okay, since they have the common solution x equals 5 halves, then the common factor is 2x minus 5. Let 3x minus 4 and 7x plus 3 be the other two factors. Then 2x minus 5 times 3x minus 4 equals 6x squared minus 23x plus 20. And 2x minus 5 times 7x plus 3 equals 14x squared minus 29x minus 15. And from this, we construct the equation absolute value of 6x squared minus 23x plus 20 equals 14x squared minus 29x minus 15. Interchanging the two expressions, we obtain absolute value of 14x squared minus 29x minus 15 equals 6x squared minus 23x plus 20. However, these two versions result in the same two quadratic equations, which are 8x squared minus 6x minus 35 equals 0, and 20x squared minus 52x plus 5 equals 0, whose solution sets are the sets containing 5 halves and negative 7 over 4, and the other one, the set containing 5 halves and 1 over 10, respectively. So this is all for now. We hope that you have learned something new, interesting, or useful. Please click the subscription button if you want to subscribe and hit that notification bell for updates about upcoming videos. God bless.